Gases. We all have gas. Don't pass it in my room. All right, so that's the what this chapter is all about. To refresh your memories, I think we're on page 2. Does that picture look like it's on your packet? Mm-hmm. All right, good. Just to remind you, solids are rigid. Are the words on your paper? Yeah. Fabulous. Fixed shape, fixed volume. You can't squish, or what's the C word? C word, yeah. You can't compress. You cannot compress a solid. It is non-compressible. To refresh your memory, solids. If I were to look at a molecular view of a solid, it kind of looks like that. They're all hooked up tightly together. Yeah. Liquids are not rigid. They take their shape from the container. Did I spell container correctly? Good. No fixed shape. They take the shape of the container. They do have a fixed volume. These are easy to measure, you know? The container. Yeah. And the molecules just kind of float around in their substance.
Do they bump into each other?
They can. They bump into each other, and they have what's called intermolecular forces. And it's the forces between the liquid molecules.
So when you take a water bottle and spin it, make a tornado, it's like they're like all going...
Yeah, exactly. All the little water molecules. Yeah. A gas is what their focus is. Gases are not rigid. They have no fixed shape and no fixed volume. They are compressible. These guys are compressible. In fact, you can compress a gas so much it'll turn into a liquid.
Oh, really?
Really, without even changing its temperature. You can squish a gas so that those molecules get close enough together that intermolecular forces kick in, and it'll go to a liquid without even changing its temperature. No, I don't have enough pressure type devices to get her done.
What about liquid to a solid?
Even more pressure.
Really?
It can be done, yes.
Awesome.
And gas, the molecules are flying around very far away from each other. The forces that exist between these molecules, we're going to say, do not exist. In order to get a force between this gas molecule and this gas molecule, they're going to have to get a lot closer together. So here's what you need to know. Is this on your paper?
No.
Gases are easily compressed. This should follow right along, Devin. You don't have to hunt around for where it is. May I see your paper, sir? So, underneath those 1, 2, 3, 4, 5, 6 pictures, write easily compressed. Gases are easily compressed. Like this picture. Easily compressed. You can squish a gas.
Can you pull it apart far enough to where they go into a liquid like a solid? Like the reverse?
No? I don't know. I'll ponder that one. They uniformly fill a container. They will spread out evenly to fill any container, no matter the size of your container. So gases will take the volume. Gases take the volume their container. No, because this water has not taken up the volume of the container. It's not uniform through it. This liquid is hanging out at the bottom. But a gas will spread itself evenly throughout the entire container. If I open the lid, I would lose the vapor. All right, now I have water vapor hanging out above the liquid. If I opened the lid, the water vapor could escape, and then eventually what would happen to the water in my liquid, in my container? It would evaporate eventually, yes. because then you allow the vapor molecules, the gas molecules to escape. But above this liquid, the gas molecules are free to move and they take up all of that space. They don't hang out in one little corner. They take up all of that space. They mix completely with other gases. So in a container like this, you're not going to have like, oh, well, the top half is one gas and the other half is another gas, provided their densities are about the same. If they have similar densities, they'll mix evenly, just the way gases roll. They exert pressure on their surroundings. That's why balloons expand. Write this down. Exert pressure on its surroundings. What do you think P sub B is standing for?
Pressure.
Balance.
Pressure of the
Balloon.
balloon. And that's why the pressure of the balloon is consistent throughout the entire balloon. It fills up its container evenly. And you can compress a balloon until it pops. Why does it pop? The pressure is too great for what? The strength of the balloon. That's why it's harder to pop a Mylar balloon than, what do you call those regular cheapo party balloons?
$1 balloons.
Yeah. Pressure. Pressure is an important concept in this chapter. If I was in physics class, I would define pressure as force per unit area. I don't know if that's on here. Yes. So in words, pressure is defined as force per unit area. I love this expression because it works really well to explain why a knife works. Yeah. Have you ever cut something with a sharp knife? This equation explains that.
There's so much pressure in one specific point.
One specific point. Okay, so what is the area, the surface area of a knife? So this number is small, correct? And if this number is small, what happens to this number? It goes up. So that's why it doesn't take a lot of pressure to get that knife to go through something, because the area is so small. A dull knife doesn't work as well. What happens to its area? It gets bigger. And if this number gets bigger, this number gets smaller. Isn't that cool? I love math. All right. In physics, they define pressure by what's called a Newton meter squared. A Newton is a unit of force. Force is equal to mass times acceleration.
So those are the units.
Yeah, Newton is a unit of force. That's how physicists define pressure. But we're not physicists. If I put Newton meter squared, combine it into a single unit, come up with what's called a Pascal. This is a unit of pressure. A Pascal is a unit of pressure. Same dude. We don't use this unit very often. I'll tell you the conversion to the unit we do use, but we don't use this very often. But you will see it. And so if you see something that says, 84 PA, PA stands for Pascal. It's a unit. So we abbreviate Pascal as PA. So if you see it, it's a unit of pressure.
Which is the one that we use?
I'm about to get there. That's a really good question. We use atmospheres. Oh, I was going to impress you and say this number, but I should have. The unit we use is ATM. Does not stand for what?
Automatic or teller.
Yeah, it does not stand for automatic teller machine. It stands for atmosphere. That's the unit we use, is atmospheres. This will be our unit of pressure throughout this entire chapter. There's a couple more we end up using. I'll get to those, but atmosphere is the SI unit, equals SI unit. So that's the unit we use most often. There's another two that I'll introduce you to, but most of the time we end up converting those to atmospheres.
What does SI mean?
The Système International metric system.
Okay.
It's not quite exactly the same as the metric system, but close enough. This picture I like because it talks about the atmospheric pressure on your head, on your arms. If you want to picture on the top of your head a column of air going all the way up to the top of the atmosphere, that's pressure pushing down on your head. And the pressure, atmospheric pressure, 1 atmosphere is equal to 14.7 pounds per square inch. So for every inch of your body, the atmosphere pushes down on you 14.7 pounds.
That's an amazing number.
I remember this.
Isn't that cool?
Is that way to memorize that number?
No. If you go out in space, do you have that pressure pushing down on you?
No.
So what's going to happen to your body?
It kind of slowly.
Not that slowly, but what does it do?
Within a few minutes, right?
It what? You won't float around without a spacesuit.
They're not used to the no pressure.
Oh, blow up.
You blow up, you look like a marshmallow in the microwave.
Brandon, go do that.
What?
On the microwave.
Oh, okay.
All right, and these are the units that we will see most often in this chapter. So 1 atmospheric pressure pushing down on you. Anyway, no, 1 atmosphere is equal to 760 millimeters of mercury. And it's equal to 760 torr. There's your conversion. That's the one we're going to use most often in this class. What is torr? Torr is short for an Italian scientist whose name I believe is Torricelli.
Yeah.
And he did a lot of work with gases and pressure. So it's sort of a nod to him. The conversion between millimeters of mercury and torr is easy. It's 1 to 1. So if I have 14 torr, I have how many millimeters of mercury?
14.
It's easy conversion. Okay, the reason we use millimeters of mercury is due to this first barometer that was ever made. And how the barometer works is this is mercury. And so we have an open bowl of mercury because we don't care that the vapors cause cancer. Yeah, it might explain why, I'm kind of weird because we played with this in my science class. Oh, look at the mercury. It's fun to bounce around. Okay, anyway. So there's mercury.
You played with it?
Oh, yeah, we didn't know the vapors caused cancer. It was fun to play with. Okay. The air, the atmospheric pressure pushes down on the mercury at 1 atmosphere. Or
764. 768.
all right. However, this is a tube. It's a vacuum tube. What does it mean by vacuum?
No air.
No molecules whatsoever. No molecules. No atoms, no molecules, no nothing. It's just empty.
How do they manage to do that?
Oh, I keep asking every year for a vacuum setup. You get a system, and it'll draw all of the air molecules right out of it. And so we can do fun things like boil water at low pressures. I keep asking. It's about $800, but I keep asking. Can I have one of those, please? It'd be fun to play with in my class. Can I have one of those, please? I keep asking. But yes, you can get an apparatus that will completely draw all of the air molecules out of the system. You cap it, you then place it into the mercury and remove the cap. So what happens is this atmospheric pressure pushes down on the mercury. And then it causes that mercury to rise up into this tube. And if you take a meter stick and measure this distance, oh my gosh, it's 760 millimeters of mercury. And that's where we get our measurement. Now, which weighs more? Wet air or dry air? Dry. Oh, sure. So think of this column of air sitting above your head that I can't draw. And in this column of air, dry air is mostly made up of nitrogen with some oxygen molecules, but it's 78% nitrogen, so let's just count it as nitrogen. Nitrogen weighs what? 28 grams per mole. Now, in this column of air, let's replace some of those nitrogen molecules with water molecules. How much does that weigh? 18 grams per mole. Oh, who weighs more? Dry air. So if the air is really wet, what's going to happen to our barometric pressure? It goes down.
Does that mean we can run faster?
I don't know. Test it.
How do we know?
Anyway, so when a storm is coming in, when a storm comes in, what happens to the pressure as they reported on the news? It goes down. You have a low front moving in.
That's how they tell if there's a storm coming?
You have a low front coming in. And really nice dry air, they call it a high front. And a high front brings nice weather. Isn't that cool?
What about wet snow? The same thing with how I would have used
Mhm.
rain.
Depending on how wet or dry that snow is, because snow can be fairly dry. All right, so that's how we get the measurements of pressure. Now today, I would like to talk about Mr. Boyle and his law. Boyle's law. Now, Boyle's law deals with two things, volume and pressure. And, you know, it's really silly, but you know how sometimes you got to say strange stuff to help things get stuck in your head? To help me remember that Boyle played with volume and pressure, and we have a law regarding volume and pressure, I always thought of Vice President Boyle.
I remember
What?
I remember this like
From 2 years ago? Good for you. So Vice President Boyle. That helps me remember Boyle deals with volume and pressure. Now, if you have a different way to remember Boyle with volume and pressure, have at it. That was my way. So, what is the relationship between volume and pressure?
Volume increases, pressure decreases.
Yes, as this picture shows. As volume, I know, increases, pressure decreases. So why does this happen
That's what I was just thinking.
to your balloon? Denver, hey, 5,280 feet. How much is that? A mile, which is why Denver's called the Mile High City. It is cool. So why does my balloon do that?
You have less pressure.
Less pressure on the outside of the balloon, allowing the pressure inside to go down. The pressure in the balloon goes down because the balloon expands. So if you drive to Denver, you think you should fill your tires to their maximum air pressure? Oh, no. Yeah, and on the way to Denver, you'll see signs. Make sure your tire pressure is a little low because as you go up that hill, the volume is going to expand. Yeah, you see blown out drivers on the way. Yeah, they've blown a tire. Oops. It is cool.
Wait, so Denver's like really high up,
It's a mile high in the sky, yes.
so their pressure.
So their pressure's lower. In fact, why do we have the Olympic training centers in Denver?
So they can have the force on them, so when they go somewhere else, it's not as hard.
Well, actually, they do that because the air is thinner up there. The air pressure is significantly lower. I think water boils at like 94 degrees Celsius there. But the air pressure is lower. So there's not as many oxygen molecules in the air.
So it's hard to breathe.
It's harder to breathe at first, but your body will compensate by increasing the number of red blood cells in your body.
So when you go away, you can breathe easier.
So then you have an increased red blood supply,
Your endurance is
which when you come off that mountain pays off.
So is that why they make those training match?
What did the training masks do?
Um,
Probably the same concept.
They do it. It's like a pressure test.
Yeah, and that's a legitimate way to boost your red blood cells. What was the biker who got in trouble for boosting his red blood cells?
The Armstrong guy?
Yeah, yeah. Because he was infusing his own red blood cells in to give him that boost of extra red blood cells so he could process oxygen more
Or
efficiently.
you could just done it naturally.
What was that?
Because the kids, like, before track meets, like, you just know, like, you look at them with their mask and you're just like, oh, I hate that kid.
Because you know what he's doing. He's trying to boost his red blood cell supply.
Does it work fast?
I don't know. You can find that out. All right, this is what we call an inverse relationship.
What is that?
Proportional. This is the alpha, the Greek symbol alpha, and it means proportional. So this is what we call an inversely proportional relationship. Inversely proportional. As one goes up, the other one goes. As one goes down, the other one goes up. Inversely proportional.
Science.
Science rules.
Definitely chemistry. It's like everything's chemistry.
It is.
So like when we were playing basketball, we were messing with we were standing by the fan, like this is chemistry.
Uh-huh. All right. I'd like to do some math for you. I don't believe this is on your paper, but I believe I gave you space for it.
Yes. Yes.
Okay. In order to turn that inversely proportional relationship into math, so we had, read that was on your paper. Was it pressure or volume I started with? Pressure. I said pressure was inversely proportional to volume, correct?
Yes.
So what I did with this is I can't turn a proportionality sign into a relationship. So we took pressure and volume and put it on a graph. And when I did that, I found it was a straight line.
Whoa.
And that allowed me to get a slope. And in this case, the slope's value was equal to K. So then I could say pressure was equal to K over V. And then I took this and put it there, rearranged it for K, the constant. The constant is my slope. Are we good with that step of how I got there? All right. Now, oops, back up. Now, for my first situation, I'm going to put subscripts of 1s on them. That is my first situation of pressure and volume. First trial, first experiment. And then I did it again. Second experiment. And guess what I found out about K? It's the same. No matter what my experiment was, K stayed the same. So that made this a true statement. K1 equals K2. Therefore, that's a true statement. Ladies and gentlemen, I'd like to introduce you to Boyle's Law. You do not need to memorize this. I will show you later how to derive it. Figure it out on your own without having to memorize it. I promise. I'll show you how to get it without having to memorize that Boyle's law is P1 V1 equals P2 V2. All right?
I'm sure it wouldn't be hard to memorize, but
So what I have in this problem is, let's see, I have a volume of 12.4 liters.
Whoa.
I have a temperature of 23 degrees Celsius. And I have a pressure of 0.956 atmospheres. Now, two things. One, though, this is hugely important what I'm about to say. Almost every one of your problems in this chapter will be of one of two types. Type 1, before and after. We have an initial situation, and we end up with a final situation. The second type of problem in this class we'll have is moment in time, where you just look, what? Yeah, in Gen Chem. And then the other is like when you look at just what's happening right now. Not a before and after, but just looking at it right now. So what type of problem is this?
Right now.
Wait,
Read the problem again.
were you changing the pressure? The temperature stays constant. So it's before and after.
This is a before and after problem. So what I'm going to do is I'm going to put little subscripts of ones, because this is like my before. Where's my pen? There you are. So 1, 1, 1. Because that's my before. I put little subscripts of 1. Now, looking at the problem again, what volume will it occupy? So V2 is going to equal X, because I don't know what that is. You can write a question mark. What volume and then look, they have a new pressure. So P2 is 1.2 atmospheres. And T2 is 23 degrees Celsius. Oh, if it stays the same,
You don't need to.
I can ignore it. You gotta make that noise when you cross it off. Okay, so do you know of a formula involving V1, P1?
P1, V1.
Okay, good. V1 equals P2, V2. Now what do I do? Substitute. I'm going to substitute my values. 0.956. I'm going to ignore units because I feel like it. 12.4 liters equals 1.2 times X. So now we just solve for X. I wonder if I have these already solved for volume. And this unit was in, so this unit has to be in 9.88 liters. Nice job, you guys. Take a minute and read through this one. I got rid of all the words. I did too. So V1, P1, P2, V2. All right, do you know of an equation? What you got?
Well, you need to take your V1, P1, so 1.5.
I'm going to do P1, V1. But you can do V1, P1 if you want. Doesn't matter.
P1, so take your P1, which is 5.6 times 10 to the third. And then you just take your P, which is 1.53, or no, this would be 1.53. Equals X.
Hold on, I got to fix that because that bothers me.
Equals 1.5 times 10 to the fourth. X.
Okay. So let's solve for X. Yeah. Nice. Are his sig figs right?
Yes.
Yes, they are. Questions?
No, but I have like a general advice. We have to make sure.
It's a really. All right, Charles's law. Charles's law deals with, I wonder what two things.
Ice, water.
Temperature.
Boiling water.
Did you read that up there?
Temperature and volume.
Temperature and volume.
TV.
All right. So what do you think?
Charlie Brown.
Charlie Brown's on TV.
Charlie Brown, we watched it on TV. The Charlie Brown TV specials. You watch Charlie Sheen most often on
TV.
TV.
I don't watch it, but I know.
But you know who I'm talking about. So Charles's law, that's how I remembered, was on TV. So what do you think the relationship is between temperature and volume?
It's directly.
It is direct. So why can't you be in Celsius? Look at that equation. Why can't we have 0 degrees Celsius?
You have 0 on the bottom.
You can't have 0 in the denominator. No. So for Charles's law, the temperature, where'd it go?
Must be here.
Temperature has to be in what unit? It must be in Kelvin.
Is it plus 360?
No.
270.
In order for Charles's law to work, in order for Pervnert to work, you have to be in
I
Kelvin.
don't remember the conversion.
So all you have to do to get from degrees Celsius to Kelvin is add 273. So let's see. So we have T1 is now equal, it was 24.7 degrees Celsius. Now it's what? 298. Okay, stop for a second. I do want to caution you guys that a lot of times in these gas problems, students will immediately see the degrees Celsius and convert to Kelvin. Hold off on that until you decide sometimes the temperature is constant and you don't have to deal with it at all. So don't just automatically convert to Kelvin, because sometimes you just don't even need the temperature. Like on that first problem, where the temperature remained constant, we could just ditch it. All right, and what in this case was V1? 1.3 liters. T2 was what? Can't have negative. But I already wrote it. All right. So what was our new T2? Hold on. 78.5 is equal to what? 195. Keeping our sig figs constant. I guess we should have had the decimal place. But that's okay. We're just going to run with it. And V2 then is X. All right. So let's see. Does it matter which goes on top and which goes on bottom? Can I do T1 over V1? Yeah, as long as temperatures stay on top, volumes stay on the bottom. Volumes can be on top, temperatures can just make sure it's consistent. So I'm going to use temperatures on top because it's on top here. But it doesn't matter. Oh, did you write it like this? 1.3 over 298? You can do it either way.
I feel like we should just do it one way.
You should know it's okay to do it either way. You'll end up with the same answer. So, what is X?
You cross multiply.
Yeah, you can cross multiply and divide. What'd you get? 0.851? 0.851 what? Good.
I didn't get the same answer.
What'd you get? 0.849?
Oh, no. I got 0.8. What do you get?
I had 0.849, but I used
I didn't round up.
Kelvin to the first decimal place.
That's what I did.
So, I mean, it's okay.
And I put 0.
Questions? Alrighty. Take a look. I'll 3, 2, 1 this. Okay, so what'd you get? You're fine. What'd you get, Devin?
2.79 liters.
2.79 liters is correct. Are we all good on that one? Nikki, you good? We got Eli on that one, didn't we? Yeah. What do you got to do? Bet you don't make that mistake again, right? Yeah. Got it, Nikki? 28, 35, 39, 47, 51. Okay. Avogadro's law. Gee, I wonder what Avogadro's going to talk about. Moles? Yeah, moles. I love Avogadro's law. It's like the no-brainer law. Because, okay, so if I have, let's see, Boyle's law dealt with pressure and volume, and Charles's law dealt with temperature and volume. And when I hear Avogadro, I think, so this is moles and volume. Yes. Well, this one is great. If I have 1 mole of a substance and a specific volume, and I double the molage, what do you think is going to happen to my volume?
It stays the same.
It's going to double. If you add more air to a balloon, when you blow into a balloon, are you adding air? So we're adding moles. What happens to the size of your balloon? It increases. So what's the relationship between moles and volume? Directly proportional. So if we add gas, we end up with more. Of course, what has to be constant here? Keeping the pressure and temperature constant.
Are we gonna have problems that they aren't constant?
Yep. And I'll show you how to get those equations. But Avogadro's law is about keeping pressure constant. Okay. Ready for the next one? Oh, look. 2 moles of gas. And if I let some air out, what's going to happen to my volume?
Decrease.
So as one goes down, the other one goes down. See? That's why I call it the no-brainer law. You let some air out, the volume goes down. Ha. And he got a law for this with his name on it. Attractive dude that he was. Not at all.
Can you show us when we're done?
Later. So this is what we call directly proportional. Okay, so guess what I did? And I left you space to write this down. Guess what I did with the number of moles and volume? Guess what I did? I put it on a graph, and what did I find out?
The slope is K.
I got a straight line, single slope, and the slope is K. So I'm going to rearrange this for K in my first lab. Well, I guess I didn't rearrange it for K yet. I did the lab once. And then guess what we did? We did it again. And guess what I found out about my Ks?
The same.
Yeah, so if I rearrange these, and put a 1 and a 2 there. If I rearrange those to solve for K, and we know that K1 is equal to K2, then what was true?
N1 over V1 equals N2 over V2.
Ladies and gentlemen, I'd like to introduce you to
Avocado.
Avogadro's law.
Avocados.
Well, I put it in green for that reason.
Avocado.
Avocados are green. So that's why Avogadro's law was in green. 3, 2, 1.
0. Is ozone gas the same thing as the oxygen?
No.
What is?
Ozone is O3.
Oh, so you would have to convert moles.
Give him a chance to read it for a second, okay?
That's
You're already there with your questions, and I think that's great, but most of them haven't read it yet, so give him a second.
Yeah, cheater.
Help you. Take a look at this. Do I now have a molar relationship? Do I even care really about the half mole?
No.
Why not? Couldn't I just use this
3 to 2.
as N1
Yes.
and this as N2?
Yes.
Because they're proportional, and I'm not interested in the moles, I'm interested in the volume. Now, stop for a second and stop working and look up here. Suppose I wanted to use the 0.5. Suppose I wanted to use the 0.5 moles, what was it, of what? Of oxygen. Can I now get my moles of ozone?
Yes.
How?
The multiple ratio.
Right, because I know that according to this equation, for every 2 moles,
3 moles.
every 3 moles of O2, I have,
2 moles
of O3.
oh. So that's 0.33? Is that my answer there? Okay.
3.
Yeah.
Continue.
Yeah. All right, so 3, 2, 1, go. Yeah.